So let's begin with our introduction to the forensic alpha model and an advanced look at Western Europe. On our agenda, we'll talk about the history of forensic fraud detection by GMI and the first model we ever created, the AGR, Accounting and Governance Risk Model. We'll talk about stock returns and fraud detection. We'll talk about some of the shortcomings of using SEC actions with respect to equity returns. That will lead us into the evolution, or the new world, of the forensic alpha model. And finally, we will look specifically at FAM in Western Europe with several optimizations. In the beginning, in 2002, we all recall the fraud epidemic apocalypse that hit the United States. Enron, WorldCom, Tyco, HealthSouth, and several other huge frauds, taking NASDAQ down from over 5,200 to below 1,500. And maybe even more remarkable, the largest accounting firm in the United States, Arthur Andersen, was shut down because of their role in several of the large frauds, including Enron. It was this event, this fraud epidemic, that was in fact the motivation behind the creation of this firm and the first model that we created. The first model we created was called AGR, the Accounting and Governance Risk Model, and it looked at the world from a forensic point of view rather than a fundamental point of view. And it was designed to do exactly one thing: to identify the fingerprint of fraud. And by fraud, we actually mean SEC enforcement actions of accounting fraud. There was no opinion here. These are factual frauds. Lucky for us, AGR was good at what it set out to do. You can see on this chart at the bottom that if we rank companies by their AGR scores, the worst-rated companies are 13 times more likely to face an SEC action of accounting fraud than the best-rated companies. It also turns out that when you have a model that can predict SEC actions of fraud, you also have a model which can predict class action litigation and material financial restatements. And this was the beginning of our firm. Before we go any further, let's talk about how we do this identification of the fingerprint of fraud. In the AGR and FAM database, we have 360 metric operations, all forensic accounting and governance related. Some examples in the governance realm would be executive insider stock sales over total equity. We'll look at the trailing 12 months and compare it to peers. And here's where I'd like to take a brief moment to remind everyone that peering is the key to everything we do in our system. We have a proprietary peering system where we go company by company and place them in their correct industries, and then bifurcate those industries by size, either by operating revenue for industrials or total assets for the financials. So we're always comparing like to like. Some of the other governance metrics we look at would be things like the number of officer changes in the trailing 12 months, perhaps something a little bit more meaty like the CEO and CFO incentive pay divided by their annual compensation, the number of interquartile ranges that is from the industry median. Some other things we'll look at in the forensic accounting realm are the metrics listed below. Now keep in mind, a metric is just a fancy word for a ratio, and it turns out in North America and really the rest of the world, ratios in and of themselves have very little value at predicting anything, good or bad. What must be done to metrics is an operation. So we will take a metric like accounts receivable over sales and then apply 3 operations to that metric. For example, a 2-year volatility measure, which is the error term from a univariate regression. And of course, we then compare that error term relative to peers. Peering is always the key. Our other metric operations include a 1-year change relative to peers and a current period industry comparison, which measures the number of interquartile ranges a firm's value is from the median. Again, always relative to the peers. I've gone in some great depth in other webinars into the metric operation computations, and I direct all viewers to some of our prior webinars to hear the details. Let's move forward in our presentation. So now let's talk about why SEC actions and a fraud model fail to capture the full picture relative to stock returns. It makes sense that if you have a model that can predict fraud, that you would have a model which can predict at the very least cataclysmic stock returns, that is, the Enrons and Tycos of the world. There are a few secrets about the SEC, though, when it comes to enforcing actions. First of all, when a company is found to be fraudulent, the SEC doesn't just put an X by their name and mark them down as a company with accounting irregularities or fraud. In fact, the SEC goes back and lists all of the quarters and all of the financial statements that were in fact a part of the fraud. The average fraud period for the SEC is in fact 10 quarters, so a little over 2 years. And while we all remember Enron, which at the time was the 7th largest market cap company in the United States, or the equivalent of Walmart today, and how Enron went to zero because of a fraud, lest we forget that Enron became the 7th largest company in the United States because of fraud. In fact, their final income statement reported $101 billion of revenue. So there's a timing issue with respect to SEC actions and fraud and stock returns. Another thing we have to address is the fact that the most recent academic research and professional research tells us that the SEC only catches about 1 out of every 7 frauds. Now, that's not to cast aspersions on the SEC. It is in fact not their duty to catch every fraud. The SEC acts as a deterrent, not a catch-all. So they'll enforce an action on a $1 million market cap company, and they'll enforce an action on the largest company in the world, like Apple, for options backdating, with the message that the SEC is watching everyone, but the reality is they're only catching a few. Now, the impact on a model trained on SEC enforcement actions is that it has an incomplete data set. In fact, it's missing approximately 85% of the frauds out there. Even further, some of the weaknesses in using a model to predict fraud to in fact predict stock returns is this implicit relationship. Just because a company is marked as having fraud doesn't mean that necessarily there's going to be a cataclysmic stock drop. And we also don't know about the timing, where some frauds are 1 quarter long, some frauds can be as long as 6 years. We also had to allow for some multidimensional interactions between factors. But maybe most importantly, the SEC only has purview over the United States, which means that when we apply our AGR model outside of the United States, so to Western Europe, Asia Pacific, and Japan, we are implicitly saying that fraud in the United States looks identical to fraud in these other regions. And that's just not true. It turns out to be about 70% right, but there are some idiosyncrasies by region that we really needed to pick up. And finally, we needed to address the way we used our univariate measure, which in AGR is the odds ratio. So here comes the forensic alpha model. We're trying to address the issues that we saw in using a fraud model to predict stock returns. The first thing we did, we used large stock moves rather than SEC actions. More specifically for Western Europe, we took data from 2006, 2007, 2008, quarterly. Took only companies between 200 million euros to 100 billion euros, and then only those companies which moved up or down 10% or more. We then ranked those companies from 1 to 200, and only took the companies from 160 to 200, so the top 20%, and the companies ranked from 1 to 40, so the bottom 20%, and used those as our training step. That means we are now explicitly modeling stock returns, rather than implicitly modeling stock returns via SEC actions. This is a good time to remind everyone that we're still using the identical repository of 360 forensic accounting and governance metrics that pinpoint the fingerprint of fraud. We haven't reinvented anything. We're simply looking at the world slightly differently. Rather than making an implicit relationship between fraud and equity returns, we're trying to make an explicit relationship between our forensic accounting and governance metrics and equity returns. The second step we did was to replace odds ratios with the Summers' D. Summers' D is a non-parametric statistic designed specifically for univariate analysis, and in fact has been around for quite some time. But the newest academic research tells us that the confidence limits for Summers' D and their differences are in fact more informative than the traditional practice of reporting only p-values. Or said differently, Summers' D is in fact a better univariate measure than correlations, tetrachoric correlations, or in our case, odds ratios. More detail on the Summers' D can be found in our white paper. Step 3, and possibly the most important, is that we can now treat each region separately. Now that we are no longer bound by the SEC's purview, that is, we're no longer bound by fraud, and we're actually looking at stock returns, we can now look at each region as a separate model. And in fact, each region has different counts of metric operations and different metric operations themselves. Each model is in fact a distinct product. In this case, we'll be focusing on Western Europe, which interestingly enough has 83 metric operations, more than any other region. And that's because of the importance of governance on Western European stock returns. The final adjustment we made from AGR to FAM was to allow for interactions. In order to make up for these interactions, and to account for them, I had to use a nonlinear classifier, and in this case it turned out that a neural network was the best nonlinear classifier for the job. Although neural networks are a bit old, and in the realm of artificial intelligence and supervised learning algorithms there are other nonlinear classifiers that may be favored, the neural network actually worked the best. An example of the interaction that we wanted to pick up would be something like a stock buyback, which could be considered good news. When combined with a CEO selling shares at the same time, now the buyback is in fact bad news. In this case, one interaction reverses the signal of a metric, and we wanted to pick that up. So we did it with a neural network, and we did it actually relatively simply. We rolled up all of our metrics after using their Summers' D into accounting scores, governance scores, and a multiplicative interaction where each accounting score interacts with each governance score. We then took these 3 nodes and created a neural network, a hidden layer with 3 sigmoidal units. These are 3 different models. They're then weighted by the model, and out comes an FAM score. So the neural network and the nonlinear classification actually isn't that complex, but it was necessary in order for us to pick up interactions in a nonlinear way. So that's how FAM was built. Let's talk about some of the guts of it, in particular, sampling, and that there's no such thing as overfitting in this model. As I said before, the in-sample I used was 2006, 2007, 2008, market caps between 200 million and 100 billion euros, and then only stocks which move plus or minus 10% in a quarter, and then only the top 20% of those and the bottom 20% of those. If you do some quick math, it turns out that this little gray box only accounts for 8% of the population, whereas these other yellow boxes account for 92% of the population. Our out-of-sample has now grown from 2009, 10, 11, and 12 to now include 2013. Having a model built on 8% in-sample and 92% out-of-sample means there is no overfitting, and in particular, if I were to label these 5 samples, A, B, C, D, and E, and give them to you randomly, you wouldn't be able to tell me which one of them was the in-sample and which one of them were the out-of-samples. The results look nearly identical. Further, because I'm using stock return percentiles rather than actual returns, we're able to eliminate the impact of market cycles. 2006, 7, and 8, the in-sample period, has a boom, a bust, and a regular year. 2009 through 2013 also has a boom, bust, and regular years. We trained on all the market cycles, we see the results on all the market cycles, and percentiles take out that effect. The final thing is an industry bias, which FAM does not have, and that comes specifically from our metric operations and the way they were built. Again, I refer you to prior webinars to see those details, but I will discuss sector bias and sector neutrality in the optimization coming soon. Now let's talk about performance. If we look at the all sample, so all companies from 2006 through 2013, so 8 years in Western Europe, between 200 million euros and 100 billion euros, we'll see that the best rated companies return 10.5% on a compounded annual growth rate, and the worst companies return negative 10% on a compounded annual growth rate. The difference between the top and the bottom is 20.5% per year. So we can see that over an 8-year period, 1,000 euros would have more than doubled in the best rated companies and would have gone down about 65% in the worst rated companies. A fair question to say is, well, how much of that is due to the in-sample? Well, let's take a look. Let's just look at the out-of-sample, 2009 to 2013, and look at the difference between the best and the worst. It's 19.3%, nearly identical. But maybe I'm choosing samples in a way that makes FAM look good. Let's try an out-of-sample that's completely sector neutral. And by sector neutral, I mean I created rankings for FAM companies first within their industries, and then through the whole population. It turns out that if you create FAM that is sector neutral, the difference between the best rated and worst rated companies, again, is 19.3%, identical to the out-of-sample if we weren't sector neutral. But there's one thing about this sector neutrality that is quite interesting and makes a major difference in an optimization, namely that if I create a long-short portfolio of the best and worst companies, purely an out-of-sample the last 4 years, but go sector neutral, we see an information ratio of 2.32. And as we know in quantitative finance, a Sharpe ratio or information ratio above 2.0 is the golden bullet. And we're seeing information ratios above 2.3 in the Western European realm when we go sector neutral. And I point out again, this is entirely out of sample, 100% untrained data. So what was the purpose of this little exercise? Pretty simple. There simply is no overfitting in FAM. Whether the model works for you or it doesn't, you will never find any evidence of overfitting. But let's go a little bit deeper. Why is this happening? Why do the best rated companies outperform and the worst rated companies underperform? We can't say it's because of a neural network or because of metric operations or because of a Summers' D or because of market percentiles or in-samples and out-of-samples. There must be some qualitative rationale behind the results, otherwise the model in and of itself makes no sense. And it turns out there are two phenomena that prevail in FAM that drive the returns. The first effect I call the black swan effect, and it's pretty simple. We define a black swan stock return as any stock that drops by 30% or more in 1 month. And if you look at the best rated FAM companies versus the worst rated companies here in a table, this is monthly over 8 years, you can see that the worst rated companies are 15 times more likely to face a 60% stock drop in a month, 15.5 times more likely to face a 50% stock drop in a month, 7.3 times more likely to face a 40% stock drop in a month, and 3.5 times more likely to face a 30% stock drop or more in a month. And if you're wondering about statistical significance, which you should be, it turns out that for each one of these numbers, the statistical significance between the best and the worst is greater than 99.999999%. In other words, with almost absolute certainty, there's a difference between the incidence of black swan stock drops between the worst rated companies and the best rated companies. It's this phenomenon, the black swan effect, that explains why the worst rated FAM companies perform so poorly. But what about the upside? The second effect we note in FAM is the positive returns effect. And this is actually pretty simple. It turns out that the best rated companies in FAM, in this case I'm looking at the top 10% versus the bottom 10%, the top rated companies on a monthly basis just tend to not go down. So 55% of the population on a monthly basis over the last 8 years for the best rated FAM companies had returns simply greater than zero, positive returns, whereas the worst rated 10% had positive returns only 47.7% of the time. Or, if you do a little math in your head, it means that the worst rated companies actually go down more often than they go up. We also remember that when the worst rated companies go down, they have a tendency to black swan. I've also broken the population up into slightly larger portfolio constructions. If we look at the top 20% of FAM companies versus the bottom 20% of FAM companies, so we're now looking at 40% of the population, you see nearly an identical result. The best rated companies just have a tendency to not go down. Again, if you're wondering about statistical significance for both of these charts, for any comparison, we're looking at significance above 99.999%. It's the positive returns effect with the black swans effect that explain in a qualitative manner why FAM is working and what it is that we are describing and understanding by modeling the opacity transparency continuum with respect to forensic accounting and governance. Let's go a little deeper. Let's go into an optimization that isolates the FAM signal. For purposes of this exercise, we used Axioma as our optimizer. First, we looked at styles, and the contributors that we looked to in style were leverage volatility, medium-term momentum, value, exchange rate sensitivity, growth, size, liquidity, and short-term momentum. We're going to minimize these risks and see how much of the FAM signal comes outside of these contributors. But before we do that, in this optimization, I determined that FAM has a unique volatility and leverage signal. Namely, FAM has a tendency to choose companies which have low volatility but outperform, or companies that have low leverage but outperform. And in this one optimization, I decided to leave these two styles unconstrained. Of course, you can run any optimization you want. This is just one demonstration, or a proof of concept. When I took a look at the contributions by style to the FAM portfolio that was long-short, we can see they sum to negative 0.08%. In other words, when eliminating the unwanted style risks, the FAM signal is 99.9% pure. FAM, when optimized, simply has none of these other styles. It is a unique signal all by itself. Moving forward, I then decided to look at sectors. Financials, consumer staples, healthcare, energy, materials, telecom, utilities, consumer discretionary, IT, and industrials. When I ran the optimization again, I found that I got 0.53% a year from sector, which of course is minimal. I can drive this sector impact to zero, which I did in a prior example. But this optimization, again, is a different proof of concept. In conclusion, when we eliminate the unwanted style and sector risks, the FAM signal is approximately 95% pure. So if your question is how much of FAM is picked up by other factors you have in your models, the answer is zero. FAM is unique in and of itself. So in conclusion, we know that the FAM signal, when optimized, has 95% unexplained by market factors of sector, short-term and medium-term momentum, value, growth, liquidity, exchange rate, and size. We know that FAM provides significant outperformance on the top side and provides significant risk reduction as well. It also provides significant underperformance for the worst-rated companies due to the black swan effect. The model was built on 8% in-sample and 92% out-of-sample, and built on a metric database that has been functioning since 2002. We also note that FAM is available only to a limited number of clients, so not to erase the signal. Thank you for your time in addressing an introduction to the forensic alpha model, specifically to Western Europe.